Welcome to Talk Tensors. Today we are opening up a file that, and I really don't say this lightly, feels like a legitimate evolutionary leap in how we think about machine intelligence. We aren't talking about a bigger brain today. We're not just adding more layers or, feeding it more petabytes of text. We're talking about a brain that just figured out it has hands.
That is a great way to put it, a really great way. We are looking at a paper titled Toolformer. Language models can teach themselves to use tools. And honestly, this one, it really feels like a turning point. It addresses the elephant in the room with large language models.
Right, the central paradox.
Yeah.
To frame this for everyone listening, we all know the deal with modern LLMs, right? You have these systems, these absolute giants like GPT-3 or Paul M.
Yeah.
They can write a sonnet in the style of Keats about, a grilled cheese sandwich. They can code an entire website in Python. They can translate Swahili to French. They have this incredible fluency.
They've mastered the statistical patterns of human language. They are, like you said, incredibly fluent.
Exactly. Fluent. But, and this is the but that drives everyone crazy, you ask one of these models to multiply, say, 4,238 by 91, and it just falls apart. It looks you dead in the eye. Metaphorically, of course, and tells you the answer is 7. Or, it hallucinates a number that looks right. Maybe it has the right number of digits, but it's just factually, mathematically wrong.
It's the smart but disconnected problem. That's what we call it. You have this massive brain, this neural network that's essentially locked in a frozen state. It knows everything that was in its training data up to a certain date, but it has no eyes, no ears, and crucially, no hands. It can't reach out to a calculator. It can't check a calendar to see what day it is. So it hallucinates answers because it's just trying to predict the next word based on probability, not on verified truth.
It's strictly relying on vibes.
Yeah.
That's all it is. Predicting the next token. And unfortunately, mathematical truth isn't always the most probable next word in a sentence if you're just looking at patterns in literature and web text.
Exactly. If the model hasn't seen that specific equation 4,238 times 91 a million times in its training data, it's just guessing. It's interpolating from things that look similar.
Yeah.
It doesn't actually know math. It knows the language of math. There's a huge difference.
And that is where today's paper comes in. The thesis here is just, it's so fascinating. We aren't just talking about, hard coding a calculator into a chatbot. That's been done. We are talking about a model that teaches itself to use tools.
That's the key distinction. That's the leap. This is the shift from just predicting text to actually taking action.
So buckle up, because we are about to dive deep into how a machine learns to acknowledge its own limitations.
Yeah.
And then reach for help.
Yeah, let's get into it. This is a good one.
Okay, so before we get into the nuts and bolts of Toolformer, help us understand the landscape before this paper dropped. Because it's not like people weren't trying to get AI to use tools before, right? This seems like a pretty obvious problem to solve.
Oh, no, they certainly were. It's been a kind of holy grail for a while now. But the methods were, clunky to say the least. Generally, you had two main camps. Camp 1 was the hard-coded camp.
The rules-based approach, like if-then statements.
Right. You'd write a rule-based system, usually using something called regular expressions that just scans the user's input. If it sees 2 plus 2, or if it detects a keyword like weather in London, it just interrupts the model, runs a little script, and places the answer back in.
Which, that works for 2 plus 2, but what if I ask, what's the square root of the number of apples I have if I have 4 dozen?
The hard-coded system just breaks. It's brittle. Completely brittle. It relies on the programmer anticipating every single possible way a user might ask for a calculation. You end up just playing this endless game of whack-a-mole with syntax and phrasing. It just doesn't scale to the complexity of real human language.
Okay, so that's Camp 1, brittle and inflexible. What was Camp 2?
Camp 2 was the human annotation camp. This is pretty much what it sounds like. It involves paying thousands of humans to sit down and write out examples. Literally, if the user asks about the weather, you should type this specific API command. You're effectively training the model through supervised learning on a huge data set of tool usage examples written by people.
Which sounds incredibly expensive.
Extremely expensive and slow and so hard to scale. What happens if you want to add a new tool, say a stock market checker? Well, you have to go back to the humans and pay them to write thousands and thousands of new examples for that specific tool. Plus, and this is a subtle point, humans don't always search the way a machine should. A human might search for best restaurant nearby, whereas a machine might need to query a database with, specific latitude and longitude coordinates. The intent is the same, but the syntax is totally different.
So we had brittle rules on one side, and expensive humans on the other. But there was also this third philosophy kind of dominating the whole field, right? The scaling law mindset.
Yes. And this was, for a few years, the dominant religion in AI. It really was. The belief was that if we just make the models bigger, more parameters, more data, more compute, these little problems would just sort of solve themselves.
Just throw more GPUs at it.
Yeah.
The bigger the brain, the smarter it gets.
Precisely. The logic was, GPT-2 was pretty bad at math. GPT-3 is kind of okay at math, therefore GPT-4 will be a math genius. But what we found, and what the whole field found, is that even the giants, these models with 175 billion parameters, they still struggle with basic arithmetic. They still hallucinate historical facts. Scaling makes them more fluent, sure, but it doesn't necessarily make them more grounded in reality.
It's like mathematical precision isn't a function of language fluency. You can be the most articulate liar in the world.
Correct. You can hallucinate with perfect grammar. So this is the world that Toolformer enters. This is a paper from Meta AI Research, and they propose something totally different. A model that learns to use API's application programming interfaces in a self-supervised way.
Self-supervised. That's the magic word here, isn't it? This means no humans labeling data and no hard-coded if-then rules.
Exactly. The model teaches itself.
Let's unpack that core concept then. What is the main objective? What are they trying to achieve here?
Okay, so the objective is to give a language model the ability to decide 4 things all on its own. 1, when to call a tool. 2, which tool to call from a list of options. 3, what arguments or inputs to pass to that tool. And finally, 4, how to incorporate the result from that tool back into its train of thought.
And they pull this off using something the paper calls the in-context trick.
Right. They're leveraging a known property of these huge models. They rely on the fact that these models are already pretty good at following patterns. If you show a model just a few examples of something, what we call few-shot prompting, it can generally figure out the pattern you're showing it and replicate it.
So they're using the model's existing ability to bootstrap a totally new ability. It's learning how to learn.
Exactly. The goal here is to create a general tool user. They didn't want to build a math bot or a calendar bot. That's the old way. They wanted a general language model that retains all its amazing poetry writing and coding skills, but just gains this specific new proficiency in reaching for external help when it hits a problem it can't solve on its own.
Okay, I want to get into the how. This is the part that really sets this paper apart for me. It's this ingenious 3-step process. Step 1 is sampling API calls. Can you walk us through what that means?
Sure. So imagine you have a massive data set of just plain text. Millions and millions of sentences from the web Wikipedia, books, news articles, you name it. The model's first job is to read through all this text and try to find places where a tool might have been useful.
But wait, how does it know where a tool might be useful if it hasn't learned to use them yet? That sounds like a chicken and egg problem.
It does, but that's where the prompt comes in. It's a clever little trick. The researchers wrote a prompt, which is just a set of instructions, that includes a handful of human-written examples. Just a few. For instance, for a question answering tool, the prompt might look something like this. Your task is to add calls to a question answering API where they might be useful. Here's an example. Input. Joe Biden was born in Scranton. Output. Joe Biden was born in QA. Where was Joe Biden born? Scranton.
Ah, I see. So they're not telling it a rule, they're just showing it a pattern. They feed this prompt to the model, which essentially primes it. It puts the model in the mood to look for facts.
Exactly. It's been shown the pattern. So then they feed it a brand new sentence from the real data set. Let's say the sentence is, the Brown Act is California's law requiring open meetings for local government bodies. Because the model has just seen those examples, it tries to mimic the pattern. It might look at the phrase, the Brown Act, and try to insert a tag that looks like API Wiki search, Brown Act API.
So it's just guessing. It's basically saying, hey, based on the pattern you just showed me, it seems like maybe I should do a search for this term right here.
It's sampling probabilities. It's not just one guess. It samples multiple potential positions for these API calls and multiple potential arguments to put inside them. It's casting a really wide net. Maybe I should search here. Maybe I should use the calculator on this number over here.
But if it's just guessing based on a handful of examples, aren't most of those guesses going to be, well, terrible?
Oh, absolutely. The vast majority will be total garbage. It might try to use a calculator on the word the. It might try to use the question answering tool on a preposition like of. It's just noise.
So now we have this massive data set, but it's full of useless, noisy API calls.
At this stage, yes. But that leads us directly to step 2, executing the API calls. The system actually takes all these text-based API calls that the model just generated, and it runs them. It passes them to a Python script or a search engine, and it gets a real result back.
So if the model happened to generate a call for calculator, 400, 1400, the system actually runs that math and gets back the text, 0.29.
Correct. And if it generated Wikisearch it gets back a snippet from Wikipedia about the definite article the. So now for every position, we have the original sentence, the API call the model guessed it should make, and the actual text result from that tool.
But you said most of the guesses are bad. So now we just have a text full of bad calculator usage and useless search results. It seems like we've just made the data set worse.
And that is why step 3 is the most critical step of the entire process. This is the filtering step. This is where the self-teaching really, truly happens. The model has to decide for itself. Was this tool call actually useful?
Okay, how does a machine define useful? Does that like a concept of utility? That seems very abstract.
It defines utility mathematically. It uses a very specific metric called perplexity. Or to put it in terms of the loss function, it's about reducing cross-entropy loss.
I see loss in every single AI paper. Let's break this down for the listener who isn't a machine learning engineer. What is loss? What does that mean here?
Think of loss as a surprise score, or maybe a confusion score. That's a good analogy. When a language model is generating text, its whole job is to predict the next word. If it predicts the next word with 99% confidence and it gets it right, the loss is near zero. The model is not surprised at all.
Okay, so low loss means the model is confident and correct. It knew what was coming.
Right. But if the model is really unsure, if it thinks the next word has an equal chance of being cat or dog or table, and the actual next word turns out to be constitution, the model is very, very surprised. The loss score is high.
So high loss equals high confusion. Got it.
Precisely. So to judge if a tool was useful, they compare two scenarios using the surprise score. In the paper, they call it $or minus and dollars plus L plus.
Okay, let's walk through scenario A, the L minus.
Scenario A. The model tries to predict the rest of the sentence without any help from the tool. It just uses its own internal weights, its own knowledge. It calculates the loss, that confusion score. Let's say the sentence is, the capital of Sudan is Khartoum. If the model doesn't know African geography very well, it might be really confused about what word comes after is. So the loss is high.
It's just guessing. It has no idea.
Right. Now, scenario B, L plus. They take that exact same sentence, but this time they prefix it with the API call and the result. So the model gets to see the answer QA result, Khartoum, before it has to predict the word Khartoum.
Ah. Well, if the answer is literally right there in the text it was just given, the model should be able to guess the next word with like 100% certainty.
Exactly. If the tool provided the correct information, the confusion score in scenario B should plummet. It should drop to near zero.
So they just compare the two scores, the confusion without the tool versus the confusion with the tool.
They look at the delta, the difference. If the tool caused a significant reduction in perplexity, meaning the tool made the correct next words much, much easier to guess, then that API call is kept. It gets a little check mark. It's labeled as useful.
And what if the confusion score stays the same or barely changes?
Then the tool didn't tell the model anything it didn't already know. If the sentence is, Paris is the capital of France, the model already knows that with near perfect certainty. A wiki search for capital of France won't reduce the surprise because the surprise was already zero. So that tool call is thrown out. It's rejected as not useful.
And what if the tool returns garbage, like that search for the word the?
Then the confusion might actually go up. If the calculator returns a wrong number or the search returns a completely random article, it makes the correct next word harder to predict. Those are definitely rejected. They increase the loss.
That is just brilliant. It's like the model develops an intuition for its own ignorance. It's filtering out things that are obvious and it's filtering out things that are irrelevant. It only keeps the aha moments.
Exactly. That's the perfect way to describe it. It only learns to use the tool when the information provided fills a gap in its own internal knowledge. It sifts through millions of these garbage calls and keeps only the few thousand that provide those genuine aha moments.
So after this massive filtering process, what are we left with? What's the final product of these three steps?
We are left with a new augmented data set. It's the same text as before from CCNet, Wikipedia, but now it's intelligently peppered with these correct high-utility API calls.
And then they just retrain the model on this new, smarter data set?
They Fine-tune it, yeah. They take the original model. In this case, it was a version of GPT-J with about 6.7 billion parameters, and they just continue its training on this new data. The model learns that these API calls are just another part of the language. Just like a comma or a period or a quotation mark, an API call is a valid token that it can choose to generate.
So when I'm using the finished model, the Toolformer, and I ask it a question, what is actually happening under the hood?
It's just generating text normally, word by word. But eventually, based on its new training, it might predict a special token. It's an arrow token. When the model's generator hits that token, it pauses. It stops generating.
It stops speaking, in a sense.
Right. The system running the model sees that special token, looks at the API call the model just typed out, executes it in the real world, calls the calculator, searches the web, and then it pastes the text result right back into the sequence. Then it tells the model, okay, here's the result. Continue generating from here.
It's completely seamless from the user's perspective?
To the user, yes. It just looks like the model got the answer right the first time, but structurally the model paused, went to the library, checked a book, came back, and then finished its sentence.
Let's talk about the specific tools they gave this thing, because the choice of tools really defines what an agent can and can't do, right? If you give it a hammer, everything starts to look like a nail.
Yeah.
They chose 5 specific tools.
Yes. And each one was very deliberately chosen to address a specific known weakness of the transformer architecture.
Okay, let's start with the most obvious one, the calculator.
A simple Python script for basic arithmetic. Plus, minus, multiply, divide, nothing fancy. But crucially, this completely solves the precision problem. We touched on this earlier, but it's worth reiterating. LLMs don't understand numbers as values. They don't. They understand them as tokens. The string of digits 100 is just a word to them, like apple or river.
So asking an LLM to multiply is like asking a poet to do your taxes by finding words that rhyme with the numbers. It's just the wrong tool for the job.
That's a very good analogy. By offloading this task to a calculator, Toolformer bypasses that entire cognitive gap. It doesn't need to know math. It just needs to know how to ask for math to be done.
And they used some heuristics here to save on training time, right? This wasn't just brute force.
Right. During that initial sampling phase, they only bothered trying to insert calculator calls if the text they were looking at actually contained at least 3 numbers or specific keywords like equation or sum. If a sentence is just, the sky is blue, there's no point in even checking if a calculator helps. That saved a ton of compute.
Smart. Okay, tool number 2, the question answering tool.
This one is interesting. They use a system called Atlas, which is a retrieval augmented model trained on a data set called natural questions. Basically, it's a factual lookup tool. It's really good for short, specific answers, dates, locations, who is the CEO of X, that kind of thing.
So how is that different from the third tool they use, the Wikipedia search? They sound similar.
It's all about the granularity of the answer. The QA tool gives you a specific answer entity. If you ask, what is the capital of Peru? The QA tool is designed to return just one word, Lima. The wiki search, on the other hand, is a BM25 retriever. That's more old school search tech. It returns short text snippets, sometimes entire paragraphs, from Wikipedia.
So the wiki search gives you the context, not just the answer.
Exactly. The QA tool is for when you need a noun. The wiki search is for when you need to understand a concept. And this is important. The model has to read that paragraph from Wikipedia and extract the relevant part itself. It's a more comprehensive tool, but it requires more cognitive work from the model to use the result.
Got it. Okay, then we have machine translation.
Right, using a big multilingual model called NLLB. This allows Toolformer to translate text from various source languages into English.
Why specifically into English? Why not just have the model learn to think in Spanish or German?
Because the base model they use, GPT-J, is primarily trained on English data. Its internal world model is constructed from English. It thinks best in English. So if it encounters a German sentence in a data set, it's actually easier for it reduces perplexity more, to translate that sentence to English first, understand it, and then proceed.
That implies a really strong English bias in the underlying model, doesn't it?
Yeah.
It finds it easier to do a round-trip translation than to just think in the native tongue.
That's a known characteristic of most of the big LLMs available today. They are very Anglo-centric. This tool is effectively a clever workaround for that inherent bias.
And finally, the calendar tool.
The simplest, but in my opinion, perhaps the most profound tool of them all. All it does is return the current date when called.
Today is Tuesday, February 18, 2026. Just a simple string of text.
Exactly. But without this, an LLM is timeless. It's completely unmoored in time. It doesn't know if it's 2020 or 2030. If you ask a standard model how many days are there until Christmas, it can't answer. It literally doesn't know what now is. It exists in this eternal void where all of time is simultaneous from its perspective.
That sounds deeply existential.
It is, but Toolformer can just call the calendar, see the date, and then potentially using the calculator tool in a chain, which we'll get to, give you the exact number. It anchors the AI in the present moment. It gives it a "you are here" pin on the timeline.
Okay, so we have the theory, we have the method, we have the 5 tools. Let's get to the bottom line. Let's talk results. Did it actually work?
It worked incredibly well. And the comparison here is really, it's a David versus Goliath story.
Right, because we are comparing Toolformer, which is built on a 6.7 billion parameter model, against the behemoth of the time, GPT-3, which has 175 billion parameters.
It's a massive size difference. GPT-3 is roughly 25 times larger. Usually in the world of AI, the bigger model just crushes the smaller one. It's not even a fair fight.
But not this time.
Not this time. Let's look at the ALAMA benchmark. This is a standard test for factual knowledge. It's basically fill in the blank sentences like the capital of Australia is.
Okay, how did they do?
Toolformer significantly, and I mean significantly, outperformed its own baseline GPT-J model. That's expected. But more impressively, it created a huge lead over the much, much larger GPT-3.
Wait, hold on. The 6 billion parameter model beat the 175 billion parameter model on a test of factual knowledge. How is that possible?
Yes. And the reason is actually really simple when you think about it. GPT-3 is relying on its own internal memory, which can be fuzzy or out of date. It's trying to remember a fact it read once during training years ago. Toolformer, on the other hand, decided to use its question answering tool about 98% of the time for these queries. It didn't remember the answer, it looked it up.
It's the difference between the smartest person in the room who thinks they remember the answer and the person who just pulls out their phone and Googles it.
Precisely. The person with Google wins every time. Access to real-time information beats static, memorized information.
What about on the math benchmarks? Same story.
Same story, maybe even more dramatic. They tested it on standard math word problem data sets like ASDiv and SVMP. Toolformer more than doubled the performance of the base model without the tools. And again, the key was that it correctly identified when to use the calculator 97.9% of the time. It learned the right context for the right tool.
It learned that when it sees a word problem with numbers, it should reach for the calculator, not try to reason it out with language.
Exactly. And for the temporal data sets, questions that depend on knowing the current time Toolformer absolutely dominated because it could just look up today. The base models failed completely. They're frozen in their training year. They're still answering questions about the current president with names from 4 years ago. It's a total failure mode for them.
This brings up the concept of scaling laws again. The paper mentions something really interesting about model size and the ability to even use tools. Can a tiny model do this?
That was a key finding, and it's super important. They found that this ability to learn to use tools in this self-supervised way only really emerges at a certain scale. For them, it was around the 775 million parameter mark.
So the really small models they tested just couldn't figure it out.
Correct. They tried this whole process on models with 125 million and 350 million parameters. They just couldn't grasp the context well enough to predict the tool calls correctly. They would call the calculator at random times or fail to use the search tool when it was obviously needed. The signal was lost in the noise for them.
So there's a kind of cognitive threshold you have to cross before you're even smart enough to realize you need help.
It kind of parallels human development, if you think about it. A baby doesn't use a screwdriver. You need a certain level of world modeling, of understanding cause and effect, before you can grasp that an external object can help you achieve an internal goal.
That is fascinating. Now, of course, it's not all sunshine and roses. The authors were very transparent about the limitations. What can't Toolformer do? What are the big missing pieces?
The biggest limitation, the one they highlight the most, is what they call the chaining problem.
Chaining? What's that?
Currently, the model cannot chain tools together in a dependent way. For example, it can't say, okay, first I'll translate this French news article into English, and then I'll use that English translation as the input for my question answering tool to summarize it.
Why not? That seems like such a logical and powerful next step.
It is logical, but you have to remember how the training data was created. Those API calls were sampled independently in the text. The model never saw examples in its training phase where the output of one tool became the input for another tool. It treats every single tool call as an isolated atomic event.
That makes perfect sense. It's a fire and forget system. It calls a tool, gets a result, and that's the end of the interaction with that tool.
Exactly. It also lacks interactivity. This is another big one. If it searches Wikipedia and the result is no page found, it doesn't know what to do next. It can't browse. It doesn't know how to scroll or click a link on the page or refine its query and try again. It gets one shot, and that's it.
It can't do what we do, right?
Yeah.
You Google something, look at the snippets on the first page, realize they're all bad, and then you try a different keyword.
No. It just takes whatever the first result is, good or bad, and tries to write the next word based on it. If the result is bad, the output is probably going to be bad. It's a very passive form of tool use compared to how a human agent operates.
And I imagine this whole self-supervised training process is computationally very expensive.
Extremely sample inefficient, that's the technical term. To find just a few thousand useful examples of calculator usage, they had to process millions and millions of documents. Most of the time, the calculator isn't needed, so you're burning an enormous amount of compute just to find those few golden needles in the haystack.
Also, the model doesn't know that calling an API is expensive or slow in the real world, does it?
Right. It has no concept of cost. It only cares about one thing: reducing perplexity. If calling an API reduces the loss by some tiny, tiny fraction, say 0.001%, it might decide to do it, even if that API call adds 5 seconds of latency for the user. It has no concept of cost or time.
So you could end up with a bot that pauses for 10 seconds to calculate 1 + 1, just because it's slightly more confident than guessing the answer, even though guessing would have been instantaneous and perfectly fine.
That is a very real risk. The loss function they use doesn't include any kind of penalty for latency or, the dollar cost of making an API call.
Despite those limitations, the practical implications here feel huge. This feels like a real concrete shift towards modular AI.
It is, absolutely. It proves that tools can be treated just like another token in the language. We don't need these crazy, complex, neurosymbolic architectures where you try to physically mash a logic board into a neural net. We just need to teach the model that API is a word it can say when it needs to. It's an elegant solution.
And it completely solves the update problem, which is a massive headache for anyone trying to deploy these models in the real world.
This is the biggest practical win, I think. If the President of the United States changes tomorrow, you don't need to retrain the massive 175 billion parameter neural network, a process that costs millions of dollars and takes weeks. You just update the single entry in the database that the QA tool connects to.
The model asks, "Who is president?" The tool checks the live up-to-date database and gets the new name. The model itself stays frozen, but its effective knowledge stays fresh.
That is the difference between building a static encyclopedia and building a web browser. It decouples reasoning from knowledge. The neural net provides the general reasoning ability. The tools provide the specific, up-to-date knowledge.
That seems like the only viable future for enterprise AI. You don't want your banking AI to hallucinate interest rates. You want it to look them up from the source of truth.
Exactly. We're moving from an AI that knows things to an AI that knows how to find things.
It's a fundamental shift in the definition of competence. Okay, let's pause there on the direct analysis of the paper. I want to pivot to something a bit more speculative. We've seen the architecture, we've seen the results. Now let's talk about where this could all go.
Okay, let's do it. I love this part.
This is our Novel Notions segment, and just a quick disclaimer for everyone listening. These ideas are purely for entertainment and discussion purposes. We are extrapolating based on the paper, but these are not real systems yet.
The important word is yet.
So reading this paper, I couldn't help but think about the limitation you mentioned, the one about chaining and self-correction. The model filters training data based on perplexity. But what if we use that same mechanism for truthfulness at runtime?
Okay, go on.
Here's my pitch. The recursive fact-checker agent.
I'm listening. That's a great name.
The paper says the model keeps a tool call in its training data if it reduces loss. What if we train a model where one of the tools is a truth API, a separate high-fidelity curated retrieval system, maybe a database of verified legal statutes or peer-reviewed medical texts?
A gold standard oracle, a source of absolute truth.
Right, but here's the twist. The model doesn't use this tool to answer a question. It uses this tool after it generates its own text. So it generates a sentence like, "This medication is approved for off-label use."
Yeah.
But before it shows that sentence to the user, it secretly feeds its own sentence into the Truth API. It calculates the loss of its own statement against the verified medical database.
So it's auditing itself in real time.
Exactly. If the Truth API comes back with high perplexity, meaning the verified database strongly disagrees with what the model just said, the model effectively deletes that thought. It backspaces. It then tries to generate a new sentence, or maybe it triggers a search to find the correct information. It becomes a self-correcting loop that physically cannot utter a sentence unless it aligns with the trusted source.
That is fascinating. You are essentially taking the filtering step from the paper's training process, but you're doing it live at inference time on every single sentence.
Yes. Imagine using this for automated legal contract generation. Hallucination is a massive liability there. You can't have a model just inventing laws or clauses. But with this recursive fact checker, the model effectively runs the red line against the actual legal code before it ever speaks.
It would be slow. I mean, you're doubling or tripling the compute for every single sentence you generate. But for high-stakes environments like law or medicine,
it would be totally worth it. The cost of being wrong is too high.
I agree. It moves that critical filter from the offline training phase, which is what Toolformer does, to the online generation phase. It creates a kind of computational conscience for the AI.
Exactly. Okay, I have one more. The paper used a calculator. That's a tool for the world of math. But the real world isn't just math. It's physics.
Okay, I like where this is going.
My second pitch. The Physics Engine API.
I love it already. Tell me more.
We train a code generation model, but instead of giving it a simple calculator, we give it access to a full-blown Unity or Mujoko physics engine via an API.
So a simulation environment becomes one of its tools.
Right. So you ask a model a question about the physical world. What happens if I drop a glass vase from 10 meters onto a concrete floor?
A standard LLM would just predict the text based on its training data. It has read a lot of stories about things breaking. It would probably say it breaks or it shatters.
But the physics engine agent doesn't just guess based on text. It generates simulation parameters. It outputs code like mass, 0.5 kilograms height, 10 meter, surface material, concrete, object material, glass. It sends the structured data to the physics engine API. The API runs a rapid microsimulation. It detects a shatter event and returns the debris field data.
And then the model's job is to translate that structured simulation data back into natural language.
Exactly. It gets the data and says, it shatters into approximately 400 pieces, with the largest fragment sliding 2.1 meters to the northeast. It gives a physically grounded answer.
That is incredible. You are effectively giving the AI an imagination,
yes,
but not a hallucinated, dreamlike imagination. It's a grounded, physically accurate imagination. A robot arm, before it decides to move a cup of coffee, could run a quick sim. If the sim says spill, the model changes the plan before it ever moves.
It's Toolformer. But the tool isn't just a database. The tool is reality itself, or at least a high-fidelity simulation of it.
That feels like the logical next step for all of this. We've started to conquer math and facts. Physics and causality are the next frontier for tool use.
Man, I want to build that right now.
Get the GPUs ready. That's going to take a few.
All right, let's wrap this deep dive up. If you are listening to this and your brain is buzzing with all these ideas, what is the one core thing you need to take away from the Toolformer paper?
I think the key takeaway is that we don't need to build one single giant monolithic brain that knows everything. That might be the wrong path. We need to build a brain that knows how to learn and when to ask for help. Toolformer proves that an AI can learn to use tools in the exact same way it learns language, by observing patterns that make the world, or the next word in a sentence, more predictable.
We are moving from the era of the know-it-all AI to the era of the resourceful AI.
Yeah.
And honestly, I think I trust the resourceful one any day.
Absolutely, me too.
Thanks for listening to Talk Tensors. We'll see you in the next deep dive.